Now we have looked at a case of having two voltage sources in series. We will now consider all the other elements that we know. Okay. So the next basic element we know is the current source. Okay. Now we can imagine connecting current sources like this, and let's say they have values I1 and I2. You will immediately notice that this connection is not permitted because Kirchhoff's current law is violated at this node. Okay. Unless I2 happens to be exactly equal to I1. Okay. If this is the case, then this whole thing is equivalent to a single current source of value I1. Okay. And if I2 is not equal to I1, then this connection is not permitted. Okay. So what this means is that if you have two unequal current sources, you cannot connect them in series, because such a connection necessarily violates Kirchhoff's current law. Okay. So next we'll look at resistors in series. So I'll take a number of resistors just for illustration. Let me put down 3 of them. Okay. Now what we want to know is what is the effective behavior between the upper and lower terminals. Okay. So for that, let me mark the voltages across each resistor and the current through each resistor, and we know that the same current flows through all the resistors because of the series connection. Okay. And so I'll call that current I. So by Ohm's law, we know that V1 is I times R1, V2 is I times R2, and V3 is I times R3. Okay. And the total voltage between these two, if I call that Vx, from our earlier discussion, we know that it's the sum of individual voltages. So Vx is V1 plus V2 plus V3, which is I times R1 plus R2 plus R3. That's the relationship between the voltage across the series combination and the current through the series combination. Okay. So one thing you notice immediately is that this is a proportionality relationship as well. The voltage is proportional to the current. Okay. And the proportionality constant happens to be R1 plus R2 plus R3. So that is the effective resistance of the series combination. Okay. So what does it mean? It means that this entire combination is equivalent to, between the two ends, a single resistor. Okay. If I mark the two ends, let me call them perhaps terminals N1 and N2. So between N1 and N2, I have a single resistor whose value is given by this whole thing. Okay. So the effective resistance of a series combination of resistors is the sum of individual resistances. Okay. Now again, this is probably a result that every one of you is familiar with. If I gave you a series combination of resistors and asked you for the total resistance, you would immediately come back with the sum formula. But the reason I spent so much time on this is that even such elementary results, you should know the reasoning behind them. Okay. So once you get used to doing something like this, that is, every result that you know, you have a reasoning behind them, and that is to say, you have a way to prove the result. Okay. Once you have that, as the concepts become more and more complicated, you will still be able to prove all of them and really get a mastery over the concepts. The reason to do this is that as the problems get more and more complicated, you should still be able to prove every step of it and connect everything, every new result to something that you know, some basic concept that you know from earlier. And from this, it's pretty obvious that if you have n resistors in series, Rn, the whole thing simply is equivalent to a single resistor whose value is the sum of resistances. Okay. So next we'll look at capacitors in series. So let me connect two capacitors in the usual way, C1 and C2, and let me mark the current I through them, and I'll mark the individual voltages V1 and V2. Okay. I know that the voltage V1 is 1 over C1 integral of the current. Okay. And I'll take the integral from 0 to t, where this is V1 of t, and I have also here assumed 0 initial voltage across the capacitor. Similarly, V2 of t, again assuming 0 initial voltage across the capacitor C2 is this, okay, with the same condition. Now, if I look at the total voltage across the combination, we know that obviously it's the sum of individual voltages. That's true for all series combinations. So Vx, which is V1 plus V2, is given by the sum of these two, which you will easily see is 1 over C1 plus 1 over C2 integral I dt. Okay. Now, you see that the relationship between Vx and I looks very similar to between V1 and I or V2 and I. In other words, this relationship also, the relationship between Vx and I also looks like some capacitor, and this proportionality constant we have in front of the integral is the reciprocal of the effective capacitance. Okay. So the nature of this relationship says that the whole thing is equivalent to some capacitor C effective, and the proportionality constant tells you how much that is. This constant in front of it should have been 1 over C effective. Okay. And that is equal to 1 over C1 plus 1 over C2. Okay. So this gives you the value of the effective capacitance. Now you can extend this to more than two capacitors. So if you have n capacitors in series, the reciprocal of the effective capacitance will be the sum of reciprocals of individual capacitances. individual capacitances. Okay. Next we will look at inductors in series. Let me start with two inductors L1 and L2 and mark the individual voltages V1 and V2 and the current through the series combination, which is I. We know that V1 is L1 times the time derivative of I, and V2 is L2 times the time derivative of I, and this total voltage Vx is V1 plus V2, which if you sum these two, you will see that it is L1 plus L2 times the time derivative of I. Okay. So again, the relationship between this Vx and the current I looks exactly similar to that of a single inductor. The only different thing is the proportionality constant in front of the time derivative of the current. Okay. So clearly, from the nature of this relationship, we deduce that the series combination is equivalent to an inductor, and the value of the inductor, let me label it L effective, is given by the sum of individual inductors. Okay. And I won't draw a separate picture for this. You have seen this couple of times before. If I have n inductors in series, the combination is equivalent to a single inductor whose value is L1 plus L2 plus Ln. Okay. This is for n inductors in series. Okay. Now these are all elementary results. What I want to emphasize is that we start from the basics, that is KCL or KVL. Here, in case of series combination, Kirchhoff's current law tells us that the same current flows through all the elements. Kirchhoff's voltage law tells us that the voltage across the ends of the combination equals the sum of individual voltages. Then we combine these consequences from Kirchhoff's current law and Kirchhoff's voltage law with the IV relationship for each element and deduce the nature of the series combination. Okay. So in all the cases we have seen so far, we have of course taken series combination of identical elements. The series combination also looks like the same element and the value is modified in some way. Okay.